So before I really dive in, I have to thank you. I have to say thank you to Edmund. Thank you very much for introducing the audience to logic programming in such a thorough way. And if any of you got lost half the way, you're still fine to follow me during the talk introducing Cascalog. So I have to give credit to Nathan Martz and Sam Ritchie as well for creating this beautiful library and for providing the examples, data sets that I'm going to be using during the talk for showing you how to apply logic programming to the domain of data processing, big data processing. So to my person, my name is Stefan Hübner. I'm a co-founder of the Clojure user group in Berlin. Franz, if you follow me, hi. So it's not only a shelter for people who just are a victim of their curious minds and they found a language nobody uses and they can't use in their day jobs. It's a group of people that just enjoy hacking, and we don't do much talking. We just try doing more dojos and just open our laptops, open Vim or Emacs and keep going. In my day job, I'm lucky, I should say, not only because I'm working for Nokia Berlin, but because I can use Clojure on my day job. What I'm doing is I'm working for the Nokia Maps team, especially, well, there are several, but I'm working for the Maps search team, which is a group of roughly 50 people spread over Boston and Berlin. And we're providing address and POI searches, category searches on maps, and nearby recommendations, like what's interesting around you. Thinking about Foursquare, all of you guys know what I'm talking about. So this is just an example of a screenshot of a Lumia device running Windows Phone. So what I'm doing, the group of people I'm working in is we are digging into data sets all these devices are producing. We search, of course, uses lots of reference data about addresses, POIs, we do geolocation, reverse geolocation. Different devices produce different kinds of data sets about user activities. And of course, in a large company, you have all kinds of different data formats, all kinds of different databases. So now, how do you deal with them? We're talking about hundreds of gigabytes, we're talking about petabytes here. So of course the question these days is we've got to use Hadoop. It's a system for very large scale data processing in the range of hundreds of gigabytes, terabytes, petabytes. You can run clusters with thousands of nodes. It's a batch processing style of data processing over a distributed file system with fault-tolerant and parallel computation. That sounds awesome, doesn't it? So everybody is jumping the bandwagon, and Hadoop's all the data, right? So there's companies large and small applying this technology to their data. They send engineers and developers to trainings. Consultancy is big business here. And, well, it really sounds cool. So yeah, I was an engineer on trainings too. And you get taught about the Hadoop MapReduce API, the Java API, and after a while you figure out that's pretty verbose, for one. It's a Java API second, which is okay. You have to think a lot about the nitty-gritty details of how to cut your data into what kind of values, keys, where you got to move your values. Should they be on the value side or on the key side in order to be able to group it later on? of course, you're almost always thinking about larger, complexer kind of queries. So you're writing a lot of code, and this code gets hard to test and hard to refactor pretty quickly. So that's not so cool. Of course, there's an answer to that. Consulting companies have an answer to that. There are tools like Pick and Hive. They provide their own query language. The language Pick provides is called Pick Latin. Hive has a SQL style of language. It's usable. It's good for people that know SQL for decades already. Pick Latin is like a more relational style of language. They have you'll be using functions that are provided by the language. They have their limits, so after a couple of days you're figuring out that you need to add stuff to these languages, to these query languages, and of course it's possible. Both of these tools have facilities called UDFs, user-defined functions, that you can implement in languages like Java, Python, shell scripts, other stuff. But you figure out they have their own APIs, their Java APIs. It's even an additional API where the MapReduce API shines through. So you're dealing with two complex and verbose APIs at the same time, even though you're just trying to cut tokens out of a sentence. And it's not really intuitive, and again, testing is possible, sure, but yeah. So really, after realizing that, then you have this shipload of data there, and you got to get answers out of it because your team is trying to train the next model for the search. You're sitting there and asking yourself, so am I supposed to work with all that? We have software development. I've done object-oriented programming for more than a decade. I know about abstraction. I know about composition and all these concepts. These languages I've just shown you, they don't really have that. So am I supposed to work with these tools for the rest of my life? Or to go with the question Vija was pondering on when it traveled the universe in Star Trek Motion Picture 1. Like after it traveled all the universe and it learned all things learnable, there was still one big question. And with the famous words of Commander Spock, the question is that all there is? Is there nothing more? Right? And those of you who believe you know Star Trek, let me tell you one thing. You haven't fully experienced Star Trek until you've seen the German original. Right, so is there nothing more? And of course, no, there is more. Cascalog was developed by Nathan Martz. I believe he started working on it 3 years ago when he was first engineer at a small company called Backtype, which is now acquired by Twitter. So Cascalog is now used within Twitter to do data analysis and data processing, and it adds abstraction and composition to what we have in the Hadoop world. It's not doing all of that itself. It's using a middle tier on top of the MapReduce API, which is cascading, developed by Chris Wenzel. It's a nice Java API for dealing for thinking in tuples when you have data and about manipulations on tuples, and it provides a workflow engine that figures out what to do in order to get you the answers you want, like which steps to take in which order. You don't have to do that yourself, and that's what Cascalog is using, and it's applying some concepts of logic programming on top of it, and that's what you've seen in Edmund's talk. So let's dive in a bit. Basically, at the heart of Cascalog query language, there is the queries, right? So we have, this is the definition of the query. We have output variables. You recognize the question mark here again, and we have a generator that produces some data. It feeds variables with values, and we in this case have a filter on a variable. So this query, for instance, returns all the persons that are younger than 30 years old, right? Yeah? One question? Okay, thanks. Yeah, if you're thinking, if you're wondering, Cascalog I forgot to mention that, Cascalog is not only useful in the Hadoop world, so logic programming can be applied locally as well. If you just want to do local data analysis, Cascalog is good for that as well. So you don't have to have this 1,000-node cluster or 13 nodes, whatever you want. It's good to go locally as well on small data sets. So logic programming is not really far away from your fingertips. Coming back to this, at the heart of Cascalog's query language, we have queries. And look, that looks pretty similar to what we've seen in Edmund's talk. Yeah, sorry. We have output variables, and we have in principle generators, filters, and aggregators, but they all look the same. If you're looking at the third line and the fourth line, the age generator and the less than filter, they look pretty much the same. It's the same syntax, and they're all called predicates, because even though less than is a function that is applied on the values, it's better to think about them as constraints on values, on variables, right? So a constraint, for instance, in this case, the value of the possible values of the age variable to be less than 30 in this example. Right, these are the predicates. So predicates can be functions, they can be filters, like we've seen in the example before. They can be aggregators in the sense that in some cases you want to functions usually apply an operation on one record at a time. Aggregators apply computations on a group of tuples at a time, like summing up something, counting records, and so on. And generators, that's what we've seen in the example before. The age is a generator. It just means provide me with some data. In this case, two-value tuples data. It can be data sitting in the distributed file system in Hadoop. It can be living locally. It could be a SQL database, a web service of some sort, whatsoever. That's not specified. It's just still, again, a function. Yeah, and now I should be switching to the examples. I'm going to use the Cascalog playground namespace that's provided with the code base. If you've seen one or two talks by Nathan Martz, you're going to be recognizing some parts here for sure. So kudos goes to Nathan. Yeah, and I might be a bit nervous because when I was presenting this, when I was preparing this, I was following the Falcon 9 launch on Tuesday morning. That was pretty impressive. And did you know that Commander Scotty's ashes was on the probe going to space? Yeah. So Scotty was finally beamed up. Yeah. But okay. Let's get to the examples. Right. So here's the example we had before. More? Other complaints? Okay. Hey? Louder, please. Okay. Let's see if I can change that. Right. How's that? Well, that was a tough one. All right, we've seen this example, right? It's filtering some data, some like records that represent persons with their age. This example is based on just a vector of two tupled values, two value tuples, so to say. I'll make this larger before anybody shouts on me again. Do you see that? Can you read that? No. Thanks. Now? Good. You see, it's a vector which holds a number of vectors with two values. So these are the records, and we have a bunch of these data sources here to play with. We have age records, we have gender again, we have the follow data set. Where is it? Yeah, it's here. So we're going to use these mainly. All right, let's execute this one. And as you see, this happens locally. There's no cluster in the background. I'm not even attached to the internet. So applying some more functions here. It's when you're talking about predicates, it's not only about filtering. You want to compute some values, and you want to bind them to some other variable as well. That's what's happening here in this example. So it's a silly example. We just multiply the value of the age, and we bind that to a new variable called double age, and we want that value in the output. And now these people are twice as old. Yeah. If you wonder what that question mark in front of here is, it's just a shortcut for defining the query and executing it at the same time. And spitting it out somewhere. It could be, again, the distributed file system, some other database, or in this case, just standard out. And that's what we're going to see, what we see down there. That's standard out. Yeah, what we could as well do, we want to constrain the age of people to be that we want to only have people less than 30 years old, but we want to know, we still want to have all people, but we want to know if they belong to the first or the second group, if they're young or if they're not young. So if you're like me, above 30 doesn't mean you're old already. So we just, what's happening here, we bind the return value of the less than function to a variable. and we put that and we put it to a new variable when we return it. We spit it out. So Alice is young. Bob is not. Chris is not. Sorry, but David, and so on. Yeah, as we've was Edmund talking about it? Let's talk about constants as constraints. Here, this is also a filter, a very specific one, even though you're not seeing any function being called. What's happening here is we use a literal or constant value to already filter on the age column in the records of this data set. So let's get back to this age data set for a second. It's tuples of two values. The first one is the name, and the second one is the age. So if we're asking for people that are 25 years old, we expect to get only David and Emily back, right? So that's what's happening here. We want only those people in the age data set that are 25 years old, right? Sounds easy. Is easy. Okay. We can put these static values not only in generator lines, but on any predicates. Here, for example, we constrain on the output of some function. In this case, we want only those people whose age or double age is 50. So we constrain on the output of some function, and yeah, well, it's going to be the same people, David and Emily again. You can imagine that these queries get larger and larger very quickly, because you have to do quite a lot of manipulations, and you're feeding in more and more data sets at the same time, because you want to join data sets. I'm talking about join in a second or in a minute. But you want to have ways to abstract away specific aspects of these queries. And that's where Cascalog shines. I mean, we've seen it already here. We can use plain Clojure functions in these predicates, and we can just add our own. There's no difference between functions you can use in predicates and normal Clojure functions. It's normal Clojure functions. So thus, having a query language in such a nice language like Clojure and an interactive environment, in addition to that, it's just opening so much more opportunities for is there another good word when you don't want to use agile? To interactively, incrementally develop your queries, your data processing code, because it is code. It's not some silly script you're developing. It's going to be run in production, and you want to make sure it's working. Testing is easy as well. I hope we get to that later. So talking about this abstractions for a minute, like let's define a function that makes this aspect of filtering people that are younger than something into a useful name, so that you don't have to like mentally think about what does this line here mean. Okay, that means I'm looking for people that are younger than some value. I'm defining a function here. Younger than, given a limit. Let's use that name. Makes it even more readable. And now I'm using this function which makes this query, I guess, a little easier to read, instead of just the less than function, and of course that works as well. So I've defined a function of my own just now. I'm using it in queries, and I'm good to go. Composability is also another feature that Cascalog adds to the table. You can define queries, and you can use them as sources for other queries. So let's say you have computed some data. Like, what do you do now? Do you put it into a database and define another function to pull it out again, or do you just want to keep going and use these queries straight away and using them, like thinking about them more like views on data than already like realized data sets? That's what's happening here. We want to find people that are young people, but who are these young people following? So we define first a query that gives us young people by the definition that young people in this case are less than 30 years old, and we're using this younger than query to now join it with another data set called follows, and we have here the join, as you can see. The join that is happening here is happening because you have like two data sets and two variables with the same name. It's essentially the same variable, so it's constraining the values on both data sets at the same time, which is a join. And well, that's quite a complex example I'm bringing here at this point. I'm also joining with the third data set to pull out the age at the same time. So Alice and David and Emily are young people, and they follow these other people down here, and we have their age here as well. So as you can see, we can abstract away certain aspects of queries. We can compose queries together in order to be able to keep them maintainable, so to say, readable. That's my main driver for using these techniques, because I mean you have to maintain them as well. When a query grows to 20 lines, which could happen if you just don't have the means to abstract for abstraction and composition, then it gets messy very, very quickly. And that's what's happening with Pig, Latin, and Hive scripts quite a lot. Yeah, let's jump over that. We have joins. I've scratched them already. Wasn't my plan initially. So here is another example to just describe what how a join looks like. It's showing that joins, compared to other languages, other data processing or query languages, where you have join statements like in SQL or in Pig Latin as well, there is no join statement. It's implicit. And it's happening because Cascalog figures out that you're feeding in values from two data sets into one variable. So there must be a constraint between these two data sets, and that's a join. And so this example gives us the people and their age and gender. Where is it? Oh, there we go. So we have the age down here, people, and the gender, F is female, M is male, obviously. Joins are implicit, that's the message. Who are people following is another example, and what's their gender. So who's following more male or female could be a question you're trying to answer here. And another interesting one would be like, do you have, are in these data sets, are there mutual friends? Like, are there people that follow each other back and forth? And that's an interesting one because what you see here is you want two people or the names of two people, and they have really two relations with each other. One follows A follows B, but B follows A at the same time, and that's exactly what's happening here. So that's a mutual join. And it's working just like that. So the only people following each other are Alice and David and Alice and Emily. And we have these return values twice because it's a cross product. Getting to aggregators, sometimes, as said, you want to do computations on groups of records, and there are some provided aggregators already. In this case, it's specific functions that you define using Cascalog library, because it needs to know that this one is happening on the so-called reduce side on Hadoop. So sum is an already provided function, an aggregator, and it just sums up the age of all the people in this age data set. So what's the age of my world, so to say. There are various aspects where you can, in the Hadoop world, usually like provide certain optimizations for the reduce sides. Like some part of a computation that should happening in an aggregator can already be done on the map side when you're still handling single values, like for instance counting is one of these, or summing up stuff. And Cascalog provides means to leverage these optimization techniques. And this is hidden again in, for instance, when you're just using the sum aggregator, you're not thinking about these optimizations. It's in there already, and so you're still you free your mind from thinking about these nitty-gritty details, and just keep thinking about the problem you're trying to answer, the questions you're trying to answer. Another one is like counting how many people, how many friends people have in our data set. That's another aggregator. It does counting, and of course, when you can count and you can sum up, you can also compute an average. Like in this example, we have people and friends. We know the age of the friends. We sum it up. We count it, and we divide the sum of the age by the count of the age, and we get an average value. Again, that's just one example of a query that's already like a bit bloated here. But we can abstract away this like this computation nicely with a nice feature called predicate macros, where we say, okay, we have an input variable which maps to an output variable, and what should be happening with values from input variables? They should be summed up, they should be counted, and they should be divided, and we get an average. So we have quite a clear concept what computing an average is here. And again, summing and counting are specific optimized aggregators, and all the optimization is still applied in your query, even though you've now abstracted it away. You're only dealing with this average aggregator by now. I'm not talking about summing and counting anymore. But still all the optimization baked into the aggregators is still applied, and which is quite nice, quite useful. So I hope you can already see the power of abstraction and composition in these examples I've shown you. Let me see if I've got some other stuff here for you. Let's talk about like the canonical example that you're going to find in every tutorial you have in about Hadoop. It's the word count example because it applies the map side and reduce side at the same time. What we have here is now a specific function, a splitter, that cuts a sentence into several records, and it you want to count the words, like you want to compute the frequencies of the occurring words. And here's a nice example already for testing your queries with local data, for instance. This is the fact macro is provided by a library called Cascalog, developed by Sam Ritchie, also working for Twitter. And you probably know Mitch already. This is just adding some nice features to be able to test Cascalog queries. And what's happening here is we have this query here that computes the frequency of words in a given data set of sentences, so to say. And let's execute that. As down there, it's true. So we have easily tested this example. And we can also use this test case here to document what this query is about to be. All right. So I think I'm going to leave it there. Thank you again, Edmund, for introducing the audience to logic programming. That saved me 10 minutes of being scared to death on the stage here. Thank you very much for listening to my talk. I hope you could get away something here. Thank you. Do you have any questions, or are you just hungry?
How do you judge the runtime requirements? Like you have a big data set and you have something you want to find out. How do you judge if that's going to take like ages or just 10 seconds?
That's hard. How do you judge how long computing a specific data set takes? The odd thing in the Hadoop world is that it's not constrained by the size of the data set. I mean, you might have a data set, a database that is 500 gigabytes large, and computing the query on this data set takes just about the same time as if it would be just 1 day worth of this year's data set, because it's 1,000 nodes that are computing the data set at the same time in parallel. So it's a quite odd. It's quite odd times we're living in here now, where when you're developing interactively using Cascalog against a Hadoop cluster, and you're used to getting feedback instantly, you don't think anymore that that the cluster in the background is crunching like a petabyte of data for you just now, and it's annoying that it's taking 1 minute. It's crazy in a way. Yeah. Yeah. Another question. Okay. Thank you. Now I can enjoy the conference.
So we come back at 2.